Recorded. Yeah, so what I was saying is, first things first, yesterday I did a review session. Also watched the review session from yesterday. I think I sent you the YouTube video as an announcement. I'll record this one and I'll send you the PDF of what I write. As I mentioned on the final, one problem will be copy pasted from this review session, another problem from the review session from yesterday. So that's 2 out of 8. And then like there are 3 which were like relatively predictable. If you just go read this Canvas announcement I had posted like a couple of days ago, where I told you like, yeah, there's going to be a problem with which is exponential of a 2x2 matrix, a problem which is identifying like the conic section. And the third problem was going to be like finding a projection matrix. By the way, in the review from yesterday, I found the projection matrix in a slightly different way than how we had done it in class. So that's actually useful to watch because it can be a little bit faster. So that's another reason why I recommend. I mean, definitely everyone should watch the video from yesterday. But in particular, that's another reason because it can give you like a faster way to find these projection matrices. By the way, everyone hears me well, just double checking. I should have started with that. Does that sound good? Everyone is able to see the iPad as well. Okay, good. So right, so like what I was saying is I also gave you like I kind of because I woke up super early because of this pain in the eye. So I gave you like a class for about which like the course is 500 points. Classwork is 100 points. I posted like on the assignment on this Hello World assignment. I posted like a number. So it's kind of like your current classwork. If you have already 100 points and there's nothing else you have to worry about, and if you still don't have 100 points, you can email me and I can tell you what else you can do if you want to reach that number. So, and then on Monday, as I said, like the idea is to just have like kind of office hours during class. And then next Wednesday, Wednesday of next week, I'll also have office hours from 1 to 4. I sent an announcement about that. So just read the announcements. Everything is on the an appropriate announcement, but that way you have all that information. So in fact, today, what I wanted to start with, just still with this projection matrices stuff. I do some problems about that. So this is actually related to, where do I have it? Let me check the PDF. Okay, this is related to problem 113 on the PDF. I won't necessarily do all of it. I will just do the important parts that I care about. The thing that I do want to clarify is that for us a projection matrix. So a projection matrix P is any matrix, any square matrix satisfies P squared equals P and P equals P transpose. Okay, so the second condition is just saying that the matrix is symmetric. So any matrix that has these 2 properties is a projection matrix for us. These are sometimes called orthogonal projection matrices, and that's kind of I think how I was calling them earlier in class. I will just avoid calling them that way because it can get confusing. So like, let me just make a remark. These are sometimes called orthogonal projection matrices. But the name can be misleading because that can be misleading because this is not saying that the matrix is orthogonal, if you know what I mean. That's why I'm just going to call them projection matrices from now on, but it can be confusing. Since P is not orthogonal in general, an orthogonal matrix in general. In general. Is that making sense? So just be careful as in terms of like terminology that when I talk about projection matrix, I mean the P square equals P and P symmetric. I don't mean anything else. Okay. So I thought this could be fun to begin with because it's a bunch of easy true false questions about projection matrices. So let's do some true false. Again, they're kind of like appearing on the, they are on kind of like related to problem 113 on the PDF. So the first true false is like, if P is a projection matrix, then this, the identity minus P is a projection matrix as well. So I'm going to call this I minus P. I'm going to call it PC. You'll see the name in a second, but it's a useful name for reasons that will become clearer soon. So what do you think? Is this well, let me give you a second to copy this, and let's think about whether this is true or not. Anyone wants to take has an idea? What do you think? So the philosophy of this course is that if you think something is false, you do have to provide a counter example, right? So you need to give me now an example of a matrix which would fail this property. And actually, that counterexample would take you a little bit of time to find because the property is actually true. So let's try to check. Let's try to see why this is true. So my claim is that this is true. And so what to say that this I minus P is a projection matrix, right? We need to check two properties. That its square equals itself, right? Remember, like the property of the projection matrix is that it is its own square, right? The matrix agrees, the square of the matrix agrees with itself, and that it is symmetric, right? Is that making sense? That that's what we need to check. Is that clear? So let's try to check. Maybe B is easier, and maybe that was not controversial when you were thinking that the property was false. So what is I minus P transpose? If you remember the properties of the transpose, is I transpose minus P transpose. The identity is its own transpose, right? And P is symmetric, right? The projection matrix is symmetric, so this just gives you I minus P. So this is good, right? Is that making sense? Now, the one that's a little bit harder, maybe less clear, is I. So what is I minus P squared? I don't know if you remember that I mentioned that to do this, you have to write it like this. That's the easiest way to write the matrix multiplication for a product. And then what can you do when you get to this point? What's the idea doing here?
We just like multiply it like normally, I guess, just keeping the order.
Right. You can distribute, I guess that's one way to say it. So you can distribute. So if you distribute, you get I minus P. That's the first distributive. And then the other two are minus P plus P squared. Right? Is that making sense with everyone? So this gives you I minus 2P plus P squared. But now what property should I use next? Of the projection matrices.
Oh, we can say that P squared is equal to P by definition.
Right, exactly. So P squared equals P. So this gives you I minus 2P plus P, and that gives you I minus P again. So this matrix squares to itself. Is that making sense? Is that okay with everyone? So that's the second property of a projection matrix that we want to check. So this means that I minus P is a projection matrix. Is that okay? So far so good. Any questions about this? In fact, we can say a little bit more, which is actually useful. So suppose, in fact, we can say more. We can say more about this. Because let's say that V is an eigenvector. Is an eigenvector of P with eigenvalue lambda. So PV equals lambda V. Anyone? Yeah, I'll definitely, sorry, just to answer the question of the private chat, I'll definitely upload everything to Canvas and send you the PDF notes. Yes. And as well as the recording. So no worries on that front. I'm currently recording actually. I don't know if anyone remembers, if you have an eigenvalue of a projection matrix, there are only two possible eigenvalues for a projection matrix, right? What were those? Lambda and lambda can be only 1 or 0, right? So lambda equals 1 or 0. Good. So my claim is going to be that V is going to be an eigenvector of 1 minus P as well. sorry, I minus P, the identity minus P, with eigenvalue. What do you think the eigenvalue should be in this case? If you had to take a guess. Maybe you should give people to work it out. Yeah, it kind of depends actually on lambda is so it depends on the value the lambda is taking. Let's try to see what I mean by this. So when you do I minus P times V, right, it's 1 minus lambda. Yeah. So yeah, that's better. Good. So you get IV minus PV, right? What is IV? That's just V because that's the identity, right? And then what is PV? That's lambda V, right? That's 1 minus lambda times V. Is that making sense? So what that means is that when so what that means is that when let me see how can I write this so what this means is that when lambda equals 1, the eigenvalue is 0 for I minus P, and when lambda equals 0, right, the eigenvalue is 1 for I minus P. So if you think about it as an on or off switch, right, that means that when this is on, the other one is off, and when this is off, the other one is on. Is that making sense? If you thought of like, because if you remember, I mentioned this, I think last time, for a projection matrix, like the eigenvalues 0 or 1 can be interpreted as true or false. So what this is saying is that, or on and off, that's actually something more like close to how an electric engineer would think about this if you thought about it this as a circuit, right? On being like the current, electric current passes through the circuit, and off that there's no electric current, for example. So when this means is that when there's current for P, there's no current for 1 minus P, and when there's no current for P, there is current for I minus P. Is that clear? So this is why I minus P is called PC, because this means complement. The C stands for complement. So it is kind of like the complementary possibility. Is that clear? So if I say I like pizza, that's either true or false. So the complementary proposition is like, I do not like pizza, right? So if I like pizza is true, I do not like pizza is false, and vice versa. Is that clear? So that's why this is kind of related to what I was saying, that these matrices can be represented. I mean, these operations of logic, like the complement of a proposition, can be represented by a projection matrix. Let's see. In fact, let's do another one which is cute, related to this. So the other one is like show that if P and Q are projection matrices, or P1, P2 are projection matrices, which commute, then P1, P2 is a projection matrix. I don't know if you remember what commute means. Commute means that it doesn't matter the order in which you multiply the matrices, right? So that's what commute means. So let's call this P, P1 times P2. We need to check that P squared equals P, right? And that P transpose equals P. Again, those are the two things that you always need to check, say that you have a projection matrix. Is that clear with everyone? That's what you need to check? So let's see why A is true. So for A, what is P squared? That's P1, P2 squared, right? But that's P1, P2 times P1, P2, right? And then what should I do? Well, what you should do is use the fact that the matrix is commute. Okay, so if the matrix is commute, you can move, like these two in the middle can be swapped. So you get P1, P1, P2, P2. So what do you get? P1 squared, P2 squared. But now what can I use to finish this up?
You can use your original definition of P1, P2 since they're
Mhm.
projected matrices. It'll just be the same as the original.
Each of them is themselves. So that just means that P squared, and that was what I'm calling P, right? So P squared equals P. Is that making sense? So that's the situation here. Is that okay? And the second property, usually the symmetry property is easier to check for matrices, for projection matrices. So that just means that what is P transpose? That's P1, P2 transpose. That's P2 transpose, right? Times P1 transpose. But then each projection P1, P2 is symmetric. So that's P2, P1. And because they commute, that's the same as P2, as P1, P2. So here I'm using that they commute. And here I'm using that each projection is symmetric. Is that making sense? So that's essentially how you check that the product of these two projection matrices gives you a new projection matrix, assuming that that the matrix, the projection is commuted. Any questions up to this point so far, so good?
I have a questions.
Mm-hmm. Yeah.
So the order of the PA and P2 can be switched.
Right, by assumption. It's not that this is not something that happens all the time. The hypothesis is that you can switch it. Yes. So only because it's one of the hypotheses of the problem, if that makes sense. So in general, P1, P2 is not the same as P2 as times P1, but the problem is telling you to assume that that does happen. Is that making sense?
Yes.
Yeah. So it is only because of this one of the conditions of the problem. So yeah, just be careful to read the hypothesis of the problem. But yeah. It is in general, it's not true that P1, P2 is the same as P2, P1. I'm assuming that that's the case because otherwise, like the proof wouldn't work, if that makes sense.
Yep, I got it.
Any other questions? Okay, in fact, we can say something even which is more interesting. In fact, I can say a little bit more. And the V is an eigenvector of P1, P2, and P2 with eigenvalues lambda 1, lambda 2. So what I'm saying in this condition is that PV is lambda 1 P1 and P2V is lambda 2V. So the claim is that V is an eigenvector of P with eigenvalue. What do you think the eigenvalue would be for P? P, remember, was P1 times P2. Any guesses of what the eigenvalue for P should be? So for V? So what is P2V? That's lambda 2V, right? And remember, constants can be taken out of a matrix multiplication, so that's lambda 2 P1V, and that is what, lambda 2, and P1V is lambda 1V. So this is lambda 1, lambda 2V. So the eigenvalue is what? Is a product of the eigenvalues, right? Is that making sense? Up to this point, so far so good. Questions about this? So remember, both lambda1 and lambda2 are either 0 or 1, right? Lambda1 and lambda2 are both 0 or 1. That's the only two possibilities that they can be. So lambda1, lambda2 is 1 only when what needs to happen for the product to be 1 if each factor is either 0 or 1. So what's the only way to get that?
Does this end up being like an and statement, maybe?
Yeah, that's where I was headed. So for the product of, if two numbers are either 0 or 1 and the product gives you 1, the only way that can happen is for both factors at the same time to be 1. So, right. So yeah, if you read this in terms of true and false, that means that the product, the proposition is true only when each individual factor is true, and that's what corresponds in logic to the operation of and. So like if I say I like cake and I like pizza, that can only be true, that the conjoint proposition, that can only be true if separately I like cake and separately I like pizza, right? The requirement is for both true values to be 1 at the same time. So P equals P1, P2 corresponds to and in logic. And so that's why sometimes this is written as P1 wedge P2, because in logic this is the symbol for an and. Okay, if that makes sense. And then is that clear? And there's like again, that's a symbol in logic for and. So let me see if I can share this thing quickly. Right. So if you go back to the PDF, that's where there's an operation for OR, which is a little bit more complicated to build using matrices, which is P plus Q minus PQ. And here again, you have to assume that the matrices commute. And then that's kind of how you can reproduce like the operations of classical logic. That's also called Boolean algebras, for those of you who end up taking a course in circuit designs or electrical engineering later in your life. And that's how you recover the truth values of them.
I have a question, like while looking at these things, I'm wondering, like, how would this make your life easier? It seems like it might make things more complicated.
No, it's just that I think kind of not sure if I mentioned it last time. The thing is, like in quantum mechanics, you kind of represent the outcomes of experiments using projection matrices. So because like kind of like a projection matrix tells you measure, like a projection matrix in quantum mechanics could be one that represents like a property called spin. So spin is like kind of like angular momentum. So one projection matrix could be like, well, the spin was measured up. That's like the classical example in quantum mechanics. Like there's this thing called spin, which is either up or down. So there's one matrix that tells you that spin is up, and that would be like eigenvalue 1, for example.
Okay.
But what makes quantum mechanics interesting is that things do not commute, which is kind of this Heisenberg uncertainty principle. So you actually have to end up using matrix. For example, you would have to use projection matrices which do not commute. So that kind of messes up the I mean, there was an approach back in the day when people were working with like interpreting quantum mechanics, which was called this quantum logic. So part of the motivation for that is that if you look at certain experiments there, like the double slit experiment or many of the paradoxes of quantum mechanics, they kind of seem to violate classical logic if you see them from certain perspective. So they were trying to represent, definitely I agree that for, this is kind of like a very elegant way, but it's kind of like too fancy to actually use it in practice just for that. But the problem is that in quantum mechanics, you do, like there was an approach to try to generalize like logic to like the quantum case. So that's what people would call quantum logic. And it kind of like the model for doing that was kind of to represent like the outcomes of experiments, like kind of along these lines. It's just that in the non-commutative case, you have to fix these definitions for and or. But then the distributive logic law, there's like, I don't know if you have taken, oh yeah, I think you took, right, like intro to math reasoning. So the Morgan laws of distributive and the failing and things like that, it becomes kind of a mess. And so if you go, let me see if I can show you, let's see, where do I have it? Firefox, where are you? Oh, Firefox. Right, you can go to Google and enter quantum logic, and then you'll see what they were trying to do there. And some examples were like these basic rules like would seem to fail. Right, kind of like how they were trying to analyze that was like using projection matrices. But yeah, this failure of distributivities was kind of like the main problems there. But yeah, it's kind of like an approach which is kind of like out of like it's not as fashionable these days because people don't like to think that you have to change the rules of logic once you go to quantum mechanics. But there are non-classical logics, that's how they're called, and this quantum logic was one of those. There are other versions like of non-classical logics. So for those who are interested in that. So yeah, but I mean, it was kind of like the main motivation for where this came from. By the way, this Stanford Encyclopedia of Philosophy is really good. If anyone wants to ever read about these topics, they have about everything. And I mean, it's kind of probably more advanced, but eventually that, like, not everything would make sense at this point. Like you do need to like take a little bit more of math classes, but like down the line, if someone wants to understand all of this, that's kind of like a good place to like check for references and things like that. But I'm just saying, like, yeah, that's kind of like the main impetus for doing it this way. But at a minimum, it's very elegant that you could represent them using eigenvalues. It's a aesthetically very pleasing thing to do. But yeah, it does have, yeah, it does have it did have like a purpose, but to do that. I just like it when there are like things that don't seem would like play any role whatsoever, and then you find out, oh, you can actually use this to do the other thing, which seems completely unrelated. You know what I mean? So it's just kind of why I like to. It's a fun way to practice some just understanding of projection matrices, but it does turn out that there was like a reason for doing it that way, historically speaking. Is that okay? So the last example, the last thing that I wanted to discuss for today was just to clarify something which may have been confusing, which about diagonalizability of matrices. So I think it's important to do this. So if you remember, what does it mean for a matrix to be diagonalizable? If you have an n by n matrix, this is diagonalizable if the matrix has n linearly independent eigenvectors. but that does not mean that the matrix requires, but that doesn't require n different eigenvalues. So the eigenvalues are allowed to be repeated, but the eigenvalues could be repeated. So, but this doesn't require n different eigenvalues. Okay, so I think I kind of, in class, all the examples that I ever did with matrix diagonalizability was like, for example, like a 3x3 matrix, and I had 3 different eigenvalues, or a 2x2 matrix, and it had 2 different eigenvalues. So I kind of owe you like an example where like, it's like, let's say like a 3x3 matrix with just 2 eigenvalues and still diagonalizable. So that's the one that I wanted to do for today. So here's an example. So if you look at this, if you do this determinant of a minus lambda I, it's going to give you something like, let's see, 2 minus lambda squared times 1 minus lambda. Okay, that's what's going to happen if you find the characteristic polynomial. In this problem, for this type of problems, if it's not so easy to factorize a polynomial, I would just give you the polynomial, the characteristic polynomial. So yeah, unless like the matrix has like, it's easy to, you know, factorize it, but I'm not expecting you to factorize cubic polynomials or something of that sort. So let's just assume that I tell you that the polynomial is this. Okay, so the thing that means that the eigenvalues are lambda 1 equals 1 and lambda 2 equals 2, right? Is that making sense? But the thing, if you notice, 2 appears in this polynomial, right? 2 is repeated twice. So this one is repeated twice in the polynomial. Is that making sense? So if you wanted to show that this matrix is diagonalizable, what you need is for this eigenvalue to have at least 2 linearly independent eigenvectors. So to make A diagonalizable, we need lambda 2 equals 2 to have 2 linearly independent eigenvectors. Is that making sense? Because the thing is that from lambda equals 1, for the other eigenvalues, it only appears 1 in the characteristic polynomial. There's no chance it will give you more than 1 eigenvector. The only one that could give you more than 1 eigenvector is the one that appears multiple times in the characteristic polynomial. So that's always like a fact that will occur. Okay. So let's just try to check what the eigenvectors for lambda equals 2 are. So when you do this, you end up with minus 3, 3 minus 1, minus 3, 3 minus 1, and minus 3, 3 minus 1. Okay, and remember that for the eigenvectors, you need to find the null space of this matrix. So you need to reduce this matrix. How can you reduce it? Well, you can do, for example, like just do, notice that the well, what, all the rows are the same, right? Like, so you can do like minus row 1 plus row 2 and minus row 1 plus row 3 into row 2, row 3. Is that making sense? So it gives you minus 3, 3, minus 1, 0, 0, 0, 0, 0, 0. Right, and there's no more ways to reduce this matrix. So the homogeneous system gives you minus 3x plus 3y minus z equals 0. So it gives you z equals, you can solve for z, that z is one to solve for because like the other coefficients are 3. So that gives you 3x minus 3y. So xyz becomes xy 3x minus 3y. And this gives you oh, sorry, this should have been minus 3x plus 3y. I think I made a mistake. Yeah, thank you. Good, thanks. And so this gives you x times 1, 0 minus 3 plus y times 0, 1, 3.
So, Professor, if we have a 3x3 eigen or 3x3 matrix, and we have an eigenvalue with like multiplicity 2, it's always going to happen that like you'll have like, I guess like one equation like with 2 variables, so then you can break it into 2 different vectors.
No, that's what I'm trying to say. So there are situations where, no, like it could have happened for, what could have happened is that you only get one eigenvector from this lambda. So what I'm trying to say is that when the eigenvector is repeated, right?
Mhm.
You can get 1 or 2, for example, because the exponent is 2. So
Okay.
if you get 2 because it's 3x3, then the other one, I mean, or let me put it this way. From this one, right? Because there's a 1 in the exponent, there's for sure one eigenvector you'll get.
Yeah.
But from this one, since it's a 2 in the exponent, you could get one eigenvector or 2 eigenvectors. That's up for
Okay.
that does depend on the matrix.
Gotcha.
So if you get 1, then you are done. You cannot diagonalize it, right? And that happens many times. But if you get 2, then you can diagonalize it. Is that making sense?
Okay, that actually makes a lot of sense. Thank you.
Yeah. No, that's what I'm trying to clarify. So if you don't, what you require is 3 different eigenvectors. It's okay for the eigenvalues to be repeated, but it's not that every time that they're repeated, they will give you enough eigenvectors, right? You kind of have to check it on the particular matrix. So that's all that I'm trying to say. And then, yeah, that basically was my point. Yeah. And then this is right. This is one eigenvector, and this is another eigenvector. And then for lambda equals 1, so now you have 2 eigenvectors. And then for lambda equals 1, you have to do a minus lambda I, which is a minus I. And what is a minus I? That gives you minus 1, 3, minus 1, minus 3, 5, minus 1, minus 3, 3, minus 1. Sorry, 3, 1. Minus 1, 0, 0, 0, 1, 0, 1. And that gives you minus 2, 3, minus 1, minus 3, 4 minus 1 and minus 3, 3 minus 2. And this one you have to reduce. So for example, you could do, what you could do, I mean, it's kind of, let's see, it's kind of a boring reduction to do, but let's try to see if we can do it. Let me do it in a slightly different way. I'll do minus row 1 plus row 2 into row 2. And then I'll do minus 2 row 1 plus row 3 into row 3. I just want to kill the last, or well, no, let me do it the old-fashioned way. I'll do minus row 2 plus row 3 into row 3 first. To get a 0 here. That's basically my goal. So here you go. Is that making sense? Yeah. And then I'll use this minus 1 to put zeros above it. So I'll do I'll do 3 row 3 plus row 2 into row 2. I'll do 3, 4 row 3 plus row 1 into row 1. Okay. And then yeah, let's see from here. Is this consistent? Well, yeah, it's always consistent. Oh, okay. Yeah, so now I'll divide row 2 by minus 3. And I'll do 2 row 2 plus row 1 into row 1. Sorry, I'm reducing this in a slightly weird way. I just wanted to avoid dividing. I just didn't want to work with fractions. That's why the reduction looks a little bit all over the place. And is this going to be enough? Huh. Yeah, let's see. Did I make a mistake reducing
I
this?
think you made a mistake on row 2 on the matrix at the top there.
Oh, you mean this one?
Yeah, I think so.
Okay, perfect. Yeah, this is okay. Let's see. Oh, right, because this is 4 row 3 plus. Oh no, this is wait. Oh, it's minus 4, right? Here it should be minus 4. Is that correct?
I think to the left of it, I think it's -1.
Oh, okay. What's going on? So I'm doing 3 row 3, right? Plus row 2. So it's minus 3 plus row 2. It becomes oh, okay. I see what's happening. Yeah. Yeah. This is why you have to be careful when you reduce these things. Like now I made a mess. Sorry about that. Okay. So I'm leaving row 3 alone. And then I'm doing 3. This is what happens when you write it backwards. So yeah. So what I'm going to do is, I have to put 3 row 3 plus row 1 into row 1. Okay, so you get -2, 0, and then 3 here gives you -3, -4. Okay. And then I need to do 4 row 3 plus row 2 into row 2. So it gives you -3, 0, and then -5. Is that better now?
Yeah.
Okay, let's hope that this was the only mistake. Minus row 2 into minus row 1 into minus. So let's do row, let's put a 1. So let's do row 1 into -2. Notice how different, like the other one reducing it was no time lost, and this one is taking forever. So like, sometimes like the different eigenvectors, eigenvalues can take different amounts of time. It is what it is, but and then okay, hopefully this now should be fine. I'll do 3. I'll do 3 row 1 plus row 2 into row 2. Okay, so I must have made a typo somewhere because the idea, like, yeah, this is not going to work the way I wanted it, but it is kind of weird. I mean, I must have made like a mistake somewhere else. Let me see first. Let me quickly check if everything is fine here. Oh my God. You must have worked. Well, I'm not blaming you, but this had to be a 0. So, right? Because this was a 1, not a -1. This is what happens when you write things like with weird symbols. So now this is fine.
Yeah, once you reduce it this way, I got eigenvector like 1, 1, 1.
Yeah. It should be 1, 1, 1. Yeah, exactly. But I'm just saying, like, notice how much of a mess this can create. So, right, and then I did minus row 2 plus row 3. Yeah, so this is it. And then I did minus row 2 plus row 3 into row 3 to, and then this becomes a 1 here actually. So this is fixed also. And then, yeah, when you do those 3, let's see. Let's see if this is better now. And so it gives you 3 minus 2. And then this one gives you -3. Okay, yeah. This is starting to look better. I think that's what you were saying, right? Yeah, because what does this say? This says that -2x minus 2z equals 0. And then this one says that -3x minus 3z equals 0. So that just means that like x equals x equals what? Z minus c. And that y equals z. So okay, so I'm getting minus 1, 1, 1, but I must have made a typo somewhere else where, oh, or what's this? Oops. This was needed a plus, sorry. Oh my god. What a disaster. No, it's fine like this. Oops. This is what happens when you try to reduce these things in real life. So, bunch of typos. Okay, and now you can, so you have, this is a third eigenvector. And with this, you can diagonalize it because you have three different eigenvectors. Is that making sense? Yeah, sorry about that reduction. The whole point is that you had the correct, for 3x3 matrix, you need three different eigenvectors. It doesn't matter if you have 1, 2, or 3 eigenvalues. You just have to check whether the eigenvalues have sufficient eigenvectors. So it's just like a thing by case basis with the matrices, but I'm just saying it's not that if the matrix has two eigenvalues, it cannot be diagonalized. Sometimes it will, sometimes it won't. It does depend on the specifics. Okay. So yeah, this is more or less what I wanted to do for today. So next time, just I have a Pikachu couple, as you may have realized. So next time on Monday, I'll just give you like come if you want to ask me other things about office hours, things like that. Help if you need help with problems. And yeah, and then we'll have office hours next Wednesday as well, extra office hours. So I'll upload the video, send you the PDF notes, and yeah, I'll see you on Monday then. If that sounds good. You too.
Thank you very much, Professor.
Bye.
One more interesting question I had for you. I saw that it's actually like a quantum course, like in the math department, like 326 or something.
Oh, the foundations of quantum mechanics, yeah.
Yeah. I don't know. Would that be anything you'd be interested in teaching?
Oh, I would love to teach it, but that one is already. This is yeah. There's always someone who teaches it. Yeah. He's really good. Goldstein. I don't know how to pronounce his last name.
Yeah,
Sheldon.
I was just
Yeah,
looking
yeah.
up.
Yeah, no, but
Interesting.
Rutgers has like this in the math department. A lot of people who do Roman mechanics, which is
Hmm.
another like this. Like there's this version of quantum mechanics where the particles have actual positions, which is weirdly enough not like in the standard quantum mechanics interpretation, like almost nothing exists before you make a measurement. So, but yeah, there's like this Roman mechanics approach where like the particles do have locations at all times, and that's called like the hidden variable. But it's a long story. But yeah, if you want to learn about that, I'm sure like you'll learn it in that book. Yeah, I mean that's actually one of the books I'm reading currently about that.
Oh,
But yeah, it's like an interesting topic. Yeah.
yeah. Any like math you think that would be most helpful? I'm sure like linear algebra is a big part of it.
Yeah, I don't know how much he will get. He may try to do it very conceptual. You should email him to check. Because if he wants to draw like the largest possible audience, I don't know how much technical details he will do. I think he will just do more like a conceptual analysis of what are the conceptual issues of quantum mechanics.
I see. Yeah, I'm taking quite a few math classes next semester, so I was thinking I
I
might be
see.
able to also take that. But maybe I'll just like check
Right,
out the
but
like.
I think he teaches us every fall anyways, but it's
Okay.
an interesting course for sure. Yeah, you should, or just check with him if he would teach it fall 24, because then it might make more sense for you to wait until then.
Yeah, I think so.
Yeah. Yeah.
Awesome. So thank you for very class. I'll email you about the multi-related
Okay.
stuff.
Yeah. Good.
Have
Okay.
a good
Enjoy
week.
your
I
day.
hope you
You
guys
too.
feel
Yeah.
well.
Yes. Let me see. Question 102. Just list the three vectors that you get after do Gram-Schmidt. Just list what happens with each vector on 102. If that makes sense. If that's okay. Just find the new vectors, yeah. That's what Peter. I don't know if you heard me. Just in case, double checking. Or if not, email me and I'll tell you.